A quantum processor can be perfectly tuned at breakfast and drifting by lunch. Its qubits are driven by analog pulses, so tiny changes in frequency, amplitude, or phase can push a long calculation off course. The usual fix is awkward: stop the quantum error correction process and recalibrate. Google has now tested a different feedback loop on its Willow processor, one that learns from error detections while the protected state remains in memory. In the next few minutes, you will see what those detections reveal, why a decoder and a controller solve different problems, and what the reported stability gains do and do not prove. Start with one logical qubit. In a surface code, its information is spread across a square lattice of physical data qubits. Other measurement qubits repeatedly check the parity of their neighbors. Redundancy is the protection: no single physical qubit carries the whole logical state. Those checks turn messy analog noise into a digital stream, no event, or a detection event when an expected parity flips. Crucially, the check does not directly measure the encoded logical information. It only exposes an error signature in a bounded region of space and time. Detection is not diagnosis. Several physical faults can produce similar signatures, so a decoder compares the pattern across the lattice and across repeated cycles, then infers the most likely correction to the logical state. It treats the symptom after it appears. Here is the useful twist. Google gives that same detection event stream a second job. One branch still goes to the decoder. The other becomes feedback for a reinforcement learning controller that changes the analog pulse settings behind the errors. One learning round works like this. The controller samples a batch of candidate policies with small, simultaneous perturbations to control parameters. Willow runs QEC cycles under each candidate. Detector firing rates become rewards. Candidates linked to fewer relevant detections score better, and the learning algorithm nudges the policy distribution before sampling again. Picture a simplified 5x5 lattice. One local pulse amplitude drifts, and red detection events cluster nearby. The decoder can still infer a correction for the present logical error. The controller compares tiny candidate adjustments and favors the one that makes those nearby events less frequent. This is an explanatory animation, not a reproduction of Google's experiment. That is the aha moment: correct the symptom, then tune the cause. The decoder protects the logical information cycle by cycle. The controller tries to reduce calibration-driven recurrence. Neither branch reads or clones the protected quantum state. Both work from classical parity data generated by QEC. On Willow, the agent managed more than 1,000 control parameters in distance 5 and distance 7 surface code experiments and a distance 5 color code experiment. These were quantum memory tests, preserve a logical state through repeated correction cycles, not run a fully universal application. Against deliberately injected control drift, RL steering improved logical error rate stability by 2.4 times. When Google combined it with complementary decoder steering, the improvement reached 3.5 times. Keep the qualifier attached. This headline measures injected drift, not every noise source a real machine will encounter. In a separate result, after expert calibration had already tuned the processor, RL fine-tuning suppressed the logical error rate by another 20%. Useful, yes, but it is still error reduction, not zero-error computing. Why might this scale? Each detector is sensitive mainly to nearby controls, so the learning problem is sparse and local. In numerical simulations, Google reached a distance 15 code with tens of thousands of parameters, and the required training iterations did not grow with system size. That evidence is simulation, not a large hardware run. There are costs. Safe exploration needs small perturbations. The agent-to-processor communication loop must become faster. And if physical errors rise above the error correction threshold, adding more qubits can make the logical result worse rather than better. So remember the split: parity checks detect, the decoder corrects, and the controller retunes. Use the 5-question claim checklist in the description and subscribe for more mechanism-first technical explainers.